Well, in conferences, as you get to go to more conferences, you realize typically they put the worst talks for the end. So that's probably a signal from Matt to me that he didn't expect much. So I'll try my best for next year to be one of the first to talk, not the last one to talk. Um, so in any case, I need to do introduction. Everybody has been doing it. I don't have a slide for it. And after watching the presentations, I realize I don't really belong here, right? I don't introduce myself. I think my work should speak for me. And I don't have a slide where I have my achievements. Maybe I don't have my achievements. Um, but I learned a lot, right? I mean, typically I go to conferences to present research. Here I see a lot of interesting stuff that couldn't be published, right? So, and I'm jealous. I want to do this too. Like, I want to hack firmware. I want to hack binaries, like look into memory dumps. And then I realize, how can you get a paper out of it? And the answer is you can't probably. They'll say, well, okay, you played. How about research, right? How about methodologies? How about results? So this is going to be a talk on the other side, right? It's going to be some research we've been doing at NYU. And NYU, people know NYU on the left side, but for people who don't, I also have a student who corrects me on my grammar and grammar mistakes, so I have to be very careful about what I'm saying. NYU stands for New York University, which I need to say it because I say NYU, people don't know what I mean. And I say New York University, and then they understand. So I'm not sure when it expands and when it should be used as an acronym. But NYU is New York University, but unlike the name, actually has global presence, right? And it's funny now we say NYU New York to specify the New York campus of NYU, even though the name says it. And with the Abu Dhabi campus, which is some kilometers away from here, but as you can see from that map, NYU has campuses all around the world, right? And our students here are privileged enough to be traveling for free to all the campuses and taking courses there. So I wish I can actually apply to NYU and be a student again, right? And then I can teach myself and give me an A. So I'm here to discuss. I'll go back to the slide, the title slide, reverse engineering of industrial control system binaries. And part of my research is on embedded security, and we focus specifically on industrial control binaries. I'll spend some time on terminology. If you don't know what industrial control system is, I'm pretty sure most of you do. Industrial control systems are controlling critical infrastructure, right? So you have your water treatment facilities, critical manufacturing, nuclear plants. Inside of them, there are computational devices that control part of the process. So you have some sensors, some actuators, and then you have those systems taking part in the control process. So a very typical ICS architecture is in that slide. You have your process, that the process is reading input, sensors, and producing actuation, right? So what's the temperature? 35 degrees? Okay, so open that valve. So I sense, and then I actuate. At the same time, you may want to have visibility over the process, and so you have an engineer overlooking what's happening, because they may be automated, but you need to have a person looking at them, right? So you have your HMI station, that stands for human-machine interface, and this is where the engineer sees, like, the boiler that receives the inputs and then produces some kind of increases the flame, so the temperature will increase. And you may or may not have remote connections. So telemetry is also important. In the power grid, you need to collect data from very far away, right? But if you have a chemical plant, then everything is self-contained. So you may or may not have remote connections to the plant. So the process of specifying its component, process means the whole thing, right? It means in case you have some desalinization process, then that means that there's something coming in, like water, and then whatever this process does, right? I cannot read English. So the process is the whole thing. There's an input and there's an output. So in desalination, for example, you get salt water, you get water from the sea, and then you produce water that can be drunk by humans, right? So that's the desalination process. So it inputs a material, something real, and outputs a product that either is going to be sold or be used in a city. So that's what we call a process. A process has when you actually do stuff, for example, when you bring water in, the first thing you need to measure is the salinity of the water, right? What's the percentage of salt into the water? And then you know how much you need to do to be able to remove the salt. So you need to boil the water, so the steam will come up, and then you collect the steam that doesn't have salt in it, and then you take it out, right? I'm just giving you a very basic example of a desalination process. So the measuring and making decisions based on the measuring happened by those controllers. Or you may have heard the term PLCs, right? So PLCs are receiving the input. So in our case, what is the salinity? That's measured by a sensor. So a sensor says that X is the salinity. And then the PLC is like a computer. It says, okay, if it's X, then you have to increase the temperature to 150 Celsius. And that is given as a command to the actuator. So the actuator is producing, is the actual actuating process. So based on the sensor input, the controller is producing the actuation, is the command for the actuation. And then the actuators are doing it, right? And then I mentioned there's also the HMI. If you are in, I mean, again, the power grid, right? You may have seen a screen like this where you have your headquarters, your control center, and your substations are very far away. So you have a screen that you can see what's happening to the process, and then you can do the remote diagnosis, understand what's happening if there's something wrong. So let's focus more on the security side. So in the past, the terms, anything that had to do with smart, anything like smart grid, smart house, smart building, intelligent transportation. I mean, there's a difference between intelligence and smartness in this world. In the past, everything was purely electromechanical, right? So your devices were receiving an actual voltage, like the sensor was producing some kind of a voltage, and then they would read them, and there was no real control, like those if statements I mentioned, right? So it was reading a voltage input, and it was producing a voltage output based purely on the relaying process. So there's nothing computer inside it, right? Nowadays, though, so those devices, you have no idea whether there was something wrong with them because they wouldn't report back. It wasn't easy to understand what they were doing, and you had no way of remote connectivity or remote control over it. So, for example, in the power grid, in the past, I mean, when I grew up in Greece, and whenever we had a power outage in the neighborhood, someone had to drive. They had to receive a call because they didn't know where this was. So you had to call the company, and they say, we have a problem here. Okay, we'll send someone. Someone was driving there, and then just open the circuit breaker, right? Close the circuit breaker. So because there was no remote way to do it. So you had to physically drive and do stuff. Nowadays, we have improved, and we have devices that are smart, right? So smart grid implies that you have IEDs, intelligent electronic devices. And those devices give you great features such as connectivity. So you can actually, instead of driving to the location, you can say, okay, can you please recover, right? You send a TCP packet, and then you get back the grid up and running, right? However, now we have the problem is this, they introduce cybersecurity concerns because you can, if you can connect to that remotely as a legitimate user, other people can connect to it. And since you can do stuff remotely, again, malicious actors may also do stuff remotely. So the ICS threat landscape has changed a lot since the introduction of those smart components. And things are bad, right? I mean, you're definitely familiar with many of these attacks. You've heard of Stuxnet. You may have heard of crash override that affected a Ukrainian power grid. And finally, there are many Ukrainians in the conference. So you may you appreciate this talk more. But it's happening, and it will happen more. And actually, it's definitely underreported, right? I'm personally confident, and it has been reported as well, that there are definitely way more incidents, but the industry itself is afraid to say it, right? Because they feel about the customer confidence. They think that they should not be publicizing that because the stakeholders will be unhappy. So there is an issue of underreporting those incidents. So we don't really know exactly what the extent of the problem is, but it's happening. Is it getting worse? Always, when I give these talks, I go to ICA CERT and I take a snapshot of the vulnerabilities of the week, because you would expect, right, how many device exits are there and how many vulnerabilities do they have. Actually, this is a snapshot since 19th of March, right, like a few days snapshot. And you can see all sorts of devices plugged with vulnerabilities. So it's bad, and I do expect it to get worse, because the security for the critical infrastructure on those devices was always, it has been dependent mostly on people not caring much, right? That's one thing. And the second thing is these vendors typically, they always love security by obscurity. So they never really publicize the microprocessor they're using, they never really publicize the exact protocols they're using, and they assume it's a good way to have security, right? But this is not the case, because now people are looking into it, and it could be like benign researchers like me, maybe benign, but also malicious people may be looking at these issues. And you can find those devices now on eBay, right? Actually, much of our research, we've been buying those devices on eBay, and as they fell off the truck or something. I don't know how the sellers find the devices, but we buy them and we try to do security analysis on them. So what we have been trying to do in this work is we're trying to really understand how security has changed in the industrial control security landscape, right? And we're trying to find ways to automate many of these things, because there's a lot of very nice automation in the IT world. So you have your Metasploit, you have your reverse engineering, you have your IDA Pro, you have great tools that help you understand security a lot, but nothing of that sort exists for ICS. And ICS are very unique for many reasons I described later in this talk. But what we've been doing at NYU in my research group, we're trying to find ways to automate vulnerability assessment for industrial control systems. So the reverse engineering part, which is the title of the talk, is exactly part of this process, right? Can you automate reverse engineering of those binaries? Because those binaries are not your standard ELF you see in Linux or Windows, right? Your P in Windows, your portable executable. They're not executable. They're binaries that have machine code, but they have to be loaded by the runtime of the PLC. So you have your PLC, let's say Codesis, and it has its own unique loader that takes that non-executable binary, loads it somehow, and then it executes in the PLC. So this is what we're trying to address. And the approach we've been following, actually, we've been trying to do the whole attacking process, right? Can we create an APT? Can we create an advanced persistent threat ourselves automatically? And then once we realize all the steps needed to create the APT, and we automate them, then we can go back and start automating our defenses and start trying to understand our defenses. To do that, we dissect how an APT works in its unique steps. So this presentation is guiding you through the steps of an APT deployment. And then we take every step and automate it. So we create a whole end-to-end tool that automates APT development. And then from that, we try to understand automation and see how we can actually create defenses based on that automatic development, the malware that can be automatically developed by minimum information. All right, so in case you haven't seen the standard chart of how an APT works, again, first you do reconnaissance, vulnerability discovery, payload design, payload delivery, and then you add with attack persistence. So I'll guide you through the 5 steps, even though the focus of this talk is number 3. But I thought, since first, it's a very long talk, right? It's 45 minutes. So I need to add more stuff. And the second is, I think it's useful for the audience to see the other parts and understand the needs for either research or solutions, because there are companies here too on the other sides as well. More specifically, what each APT stage means: reconnaissance is gathering information about the target. Vulnerability discovery, you either identify existing, because in those systems, actually, ICS, they don't really get updated regularly. So 0 days are great, but you can even find like existing vulnerabilities and use them. We rarely see upgraded devices. Vulnerability discovery is the second part. Payload design. You have to create your design. Typically in the IT world, we see design that aims to do privilege escalation or some kind of denial of service attack or installation of a rootkit. In this world, that malware is a bit more sophisticated, right? It may look directly in the process and try to change the parameter of the process. For example, you have a PID controller, it will try to change the P, the proportional, from 0.1 to 0.11. And the malware should know what that means, right? So here we're talking about more than just those services. We're talking about being able to change very unique parts of the process and then see how the process reacts. Payload delivery, there are many ways to deliver your payload, right? I mean, Stuxnet, the people said they left some USB, and then that USB found its way into the to the plant, to the uranium enricher plant. You may have malware that comes from the internet. You may have USB sticks. There are many ways to infiltrate within the process, but that's out of the scope of this talk. And attack persistence, right? In this, remember, Stuxnet stayed there for a long time. We're not really sure how much crash override stayed in the Ukrainian infrastructure before manifesting itself. I'm pretty sure it has been many months, but that's my guess. We haven't heard much about it. But the fact that it was triggered at an exact time means it was ready a long time before, right? My guess would be many months. So the attacks are there and they're staying, and they may be doing damage over time, or they may be triggered at a very specific time known only to the attacker. So let's slowly walk through the steps. So reconnaissance means that you need to understand the system you're in, right? You're trying to understand what is my current industrial control system, what is the process, what is the device I'm in. Because if you make this automated malware and it spreads, Stuxnet was extremely unique. It was targeting step 7, right? And we know, most of us know why this was the case. But if you want to fully automate this, you need to be able to fingerprint on the spot. You need to be able to understand. You cannot just ask a device, what device are you, right? I'm a Siemens, I'm a Rockwell, I'm an Allen Bradley, I'm a General Electric. You need to be smarter than this and automate this to an extent. So fingerprinting starts with device identification, and that will give you further information, right? Because if you know the device type, then you can look up the firmware, and then you know the firmware, again, is typically outdated, right? So you know the exact vulnerabilities of that firmware. So the first step is to identify the device. And when you're, again, a malware that you're trying to do this automatically, you see the PLC as a black box. So you talk to it, and you get some response back, and from that process, you're trying to ask it meaningful questions to get meaningful answers back. So this can be done over the network as well. As an example of some of our work we've done, so Modbus, for example, is a good case, because Modbus is a protocol that's not standardized. That means that every vendor implements it very differently. And, well, security is out of the question. I actually had a slide explaining why Modbus is not secure, but I think it would be boring. Everybody knows the industrial protocols were never made with security in mind. They were made for robustness, right? Make sure that I get the message and I get the response. That's it. Now we have to encapsulate, we have to do SSL over Modbus, right? So you do VPN over Modbus, with VPN tunneling, in order to achieve security with industrial systems. So in case of Modbus, what we've realized is that every vendor is doing a very different thing with Modbus. So when you want to ask questions, who are you? Modbus kind of had its own way of identifying the device, but nobody's really following it. They're having their own implementations. And that gives us the opportunity to identify vendors based on the unique implementation of each vendor, right? For example, in our case, so that's the example of the WAGO, right? And the WAGO says in its manual that the Modbus register in address 2020, it gives you a short description of the controller. This is not standard. Every PLC is doing a different thing. They put their own unique identification to a different register. So I know if I'm asking 2020 and I get something that looks like a string, that's probably a WAGO. And actually, when you get it back, it says WAGO clearly, right? But even if it didn't, you'll be able to extract information about, given on what is the type of data you get back from the PLC. More details, you can read the paper. So through that, we're able to fingerprint a lot of PLCs from WAGO, from Eaton. And if you see, again, that's the comment I made, right? This, again, device, not just PLCs. So every vendor is actually putting information about the device in a different register. So by asking the right register, getting all of them, then you see different things. You can quickly say that's a WAGO, that's an Eaton device, or that's something else. So in our work, we managed to, well, we did introduce, actually, we introduced that to Shodan as well. We sent an email to John Matherly and we said, well, you have, actually what Shodan did, Shodan was only following the protocol, right? Modbus, the Modbus protocol said it's only one register you should ask. Because every vendor did whatever. Shodan was only indexing the Schneider Electric because Schneider acquired Modicon that made the Modbus protocol. So only Schneider Electric was showing up in the Shodan results. So we talked to the guy, to Matherly, and said, look, you can actually fingerprint way more accurately if you ask questions to other registers. And then actually that was implemented by him, and you can find more devices now, right? So as a proof of concept, we did 5 vendors because it's not productive user PhD time to be looking at manuals and seeing. So this is the difference here, right? This is not really research if you have people reading manuals to find numbers, right? So we just did that as a proof of concept, and we realized Modbus and asking for registers is a proper way of fingerprinting. And these are the results that, what we've seen from Shodan that appeared after we changed the way the engine works. So after we know what device we're in, now we need to find vulnerabilities in the device, right? And there are many ways of doing it, but what we mostly focus on. So there's a difference in the way we see security, right? In many of these events I go to a Black Hat, typically there's one person talking about one device, right? For us, we want more than that. We want both the device, we want the software, we also want the process. So we want a more complete assessment environment. In our case, we have something we call hardware in the loop, because we do want the accuracy. If I give you a power grid device and you hack it, right? You say you hacked it, that doesn't mean anything to me. What exactly can you do in the power grid, right? Because I see talks saying I can cause a blackout in New York City. Well, I know that you probably can't. And you can't because the power grid is robust on its own. It has been built to be robust because nature is the major attacker of the power grid, right? You have trees falling on the power lines, you have thunderstorms, you have squirrels, like either falling into equipment or eating equipment, and animals actually are more dangerous than humans for the power grid. So for us to do an assessment, we want to understand the process, not just hack the device, right? Also have the process in place. However, you cannot just go to the power grid and say, okay, hey, can I try hack your device while it's connected? Well, everybody will say no. That makes sense. So we do what we call hardware in the loop test bed that combines both, right? That you have hardware and software and the process simulated in a lab environment. So for us, we think of, we have the hardware device that will typically appear in the actual environment, and then we connect it to a simulation model. So let's say in the desalination process, right, we have, let's say we take 22-stage, multi-stage flash desalination model, and then we take one stage out and we put it in a PLC. That means that there's data coming through the stages. So instead of this, and MATLAB can model that, right? It receives something, has a PID controller, and produces an output. So instead of the PID controller being in MATLAB, I take that stage out and I run it through my PLC. So the inputs are given to my PLC, the PID is in the PLC, computing stuff, and then the output is fed back to the simulation. So by doing that, I introduce hardware in the loop. It's a closed loop, right? And if I attack the hardware now, I can see the effect in the actual process. So that gives me the ability to do process-aware analysis, right? Because I don't want to say I hacked the device. I want to say I can do this with this device. I can create a blackout. I can actually change the desalination part to produce like less brine and more like saline water, right? I can do stuff meaningfully. And to do that, we have a host PC. Actually, well, we now don't have the setup out, but the hardware CTF had many of these devices, right? So if you miss that, you can come by NYU Abu Dhabi anytime, and we'll have the testbed there in place. But to do that, we have a host computer that has the MATLAB simulation model. And then through a data acquisition device, like a compact Rio, we connect to the PLC, and the PLC has part of the control loop, right? So we run through analog So digital to analog, and then analog digital goes back, and we have the test bed in place. So what Marius had on the table there, the WAGO device. In this example, it's controlling the chemical process we have. So in this, that's a Tennessee Eastman benchmark, and this simulates like a standard chemical process. It gets some gases as an input and produces some kind of a material and some byproducts that come out with it. So we have the simulation of the chemical process in place, and some loops, like some PID control is taken out, run through the WAGO, and you will put it back. So we can show attacks like you increase the temperature of a reactor, or you increase what's happening with the output. So the part of the payload design is what we focused on, and I'm going to focus on this talk. So you found, first step, you know the device you're in. Second step, you find vulnerabilities somehow, right? There are other ways we're doing that, but I skip a lot of things. Now you have to do something meaningful, right, while you're in the PLC. Now you have to know how PLC exactly works. And PLCs, for people who don't know, you can think of them as regular computers that do a thing over and over again, right? It's like a mini computer that does one thing over and over. And it has industrial strength. That means it can withstand like higher temperatures or lower temperatures. It can withstand high voltages. So it's like a computer that's robust for the application. So to program that computer, again, we don't let people write C++, right? Because first, they can't. They're process engineers. They don't know how to code in Python or C++. And second, it's pretty dangerous to write. Any code in C or C++, it is begging for problems. So instead, you have your high-level languages like ladder logic, functional block diagram, structured text, instruction list. These are examples of high-level language used by process engineers. And they write the language, they write the program like a controller in that kind of a form. It's been compiled, and that program is going to the PLC. So this is where we come in, right? This compiler is taking high-level language and producing machine code. That's assembly. And those compilers are not your vanilla GCC, right? It's not a compiler that has been tested heavily by the open source community, right? Or by people like you here. I've seen a lot of work on understanding the security of GCC. This is proprietary stuff that nobody knows how it works. Nobody has ever assessed the security of these things. And this may be producing really bad code that we don't know of because it's not open source. So this compiler is producing some kind of machine code that the PLC runtime is taking it and using it for the process. So this is what we're trying to do here. We're trying to take those binaries and understand them. So to automate, since we're talking about automation in this talk, we need to understand what the binary does, right? That's the first thing. What part is the loop? What part is the prologue? What is the epilogue? Where are the memory maps? So to do that, we need to understand what the binary does. We need to identify the functions like PID, because we only have a blob of hex data, right, of binary bits. Then we need to somehow make sense of it. Identify the functions, and then we have to see what can we do, right? What is the p value you can find in the binary? What is the integral value? And then change something and repackage the binary. So the motivation why focusing on ICS binary, again, reverse engineering ICS binary is a double-edged sword, right? It can be used for good purposes, it can be used for bad purposes. On the good side, you can analyze PLC malware because they do target PLC. They may target PLC binaries. And second, also, sometimes there's code running on the PLC. Nobody knows where it came from, right? Those devices stay there for 20, 30, 40 years. And then someone says, and what is this doing? Nobody knows what it's doing. So you can actually use it for forensics or for recovering your control because you're not really sure. And it's not only that. Sometimes the very unique tweaks you do to a process, whether P is 0.11 or 0.101 can make a huge difference. And you have to really play with the parameters and fine-tune them to the exact digits that are 7 digits long, right? The precision. So you need to recover back your parameters because you had this guy who optimized your process, and now he's left, or he's dead, or he cannot give you back the parameters, right? You need to take them out yourself. So on the bad side, you can create what I've been discussing this time. You can create payload dynamically, or you can, and by having the sophistication of the automated analysis, there's no need for command and control, right? You can actually make decisions locally. When you're in the process, you can stay in the air gap and still do meaningful damage. So for people who reverse engineer, and I'm not sure how many are here, ICS binaries are not your typical binary, right? I mentioned that before. It's not your standard ELF that you load in IDA Pro. Their model actually is an infinite loop. They don't stop. There's no terminating condition. They never exit, right? So if you try to do symbolic execution, you realize actually it never ends. So you have an endless scan cycle, as it's been called. So in every cycle of the process, every process has its own cycle, you have a loop that runs over and over. So that's very unique about ICS. They never stop. Those binaries never end. Second, they're heavily rely on input and output. Because as I keep saying, and you're probably tired by now, they receive an input and produce an output, right? This has been done by the sensors and produces output to the actuators. And these things are memory mapped. So you see a lot of things coming from the I/O. And typically, it's very hard to do security analysis while the binary does nothing if it doesn't receive memory mapped inputs, right? It's very hard to do proper security analysis on that with symbolic execution or any other way. The file formats, they're custom and proprietary, again, security by obscurity on behalf of the vendors. Everyone does a different thing, and they believe, again, I'm not the one to judge, but by my tone, you understand I'm criticizing, security by obscurity is a good thing, right? Not sharing how this works means they're protected. But most of us here, I guess, know this is not the case. The last thing that's unique, but it's unique and helps us, is those binaries have no optimizations. In GCC, you can turn optimization on 1, or 2, or 3 to get more aggressive. People want this to work. They don't care about its performance. They want it to be robust, and they don't really trust optimizations. Like, I don't want you to delete dead code. You may be wrong. Actually, this never ends, so it's very hard to know what dead code is. I don't want you to change the variables from integers to bytes because they can shrink. No, don't touch anything. No optimizations. And that's good for us because it's much easier to reverse engineer them. So to do that, there are 2 steps. One is to do what the vendor should have been giving us, which is knowledge about the format and the binary. Now we have to do it ourselves as a one-time cost. But on the other hand, there are not really that many vendors that do it, right? There's Siemens with their Step 7 platform, there's Allen Bradley, that they have their own thing, and then Codes is pretty much the poor vendors, right? People who don't want to have their own tool chain, so they rely on something that's open source out there, not open source, but you can rent the tool chain and use it, right? Instead of building your own compiler, just take the one that works already and use it in your own company. So there are not that many numbers of platforms, so we can use, we can do this manually. You don't need to automate that part. You can see and you can add it to our tool. So the second phase is to actually, what happened dynamically, right? The actual analysis that we do in the binary, and we'll see exactly what we do. So we have a tool that we published. Again, I'm not selling anything, right? That's open source and free. Props to my student for doing it. He actually did all the work, and I'm here taking the credit for it, but that's a very common PhD advisor, PhD advisee interaction. So Tassos did all this work I'm presenting here. He's now working for Red Balloon Security in New York. So he created a tool that we published and DSS, and it's open source on GitHub. I don't have the GitHub link, sorry. It's going to be, the GitHub link is at the end. You can load a binary, a PLC binary to it, and it can dissect it for you. So what it does, it takes this that cannot be opened by IDA Pro or Ghidra, I guess. We haven't tried it yet, but why would it work? And then ICSref, as we call the tool, gives you something like this back, right? So it reads the binary and reconstructs its control flow graph, and it also creates meaningful names for your static libraries. It also creates, it gives you the interactions between what's happening. So you can clearly see this is the main loop, right? Going to the fixed cycle, and then from this, you can understand that's a PID controller. Actually, that looks like a DI controller. So now you know nothing about the binary. Now you can see a lot of things, right? To do that, which is the technical part, I'll go quickly through that. So ICSRF can understand the binary subroutines. It understands dynamic and static functions. It gives you back the physical input-output. It gives you the call graph. And as a case study, we're actually producing PID arguments that you can see and you can change by inline patching of the binary. So you can take a binary and change its p-value and give it back to the PLC, which can create an automated attack. So a binary, again, remember PLC binary may not be executable, but it does have machine code that executes on the CPU. And the loader, the unique runtime of each vendor, is loading that machine code into the main memory. So in our case, the PRG binary, the control binary, these are the steps, these are the things we found ourselves by manual reverse engineering. So it starts with some offset and then some support subroutines, debugger handler always, and then you have statically linked functions, right? So these come from, like C++, you have your STD, or C, STDIO. In those environments, you get your own blocks you can use. So like a PID, you don't have to program it. You can bring it from the library. So this is bringing things from the library. These are what the user does. User-defined blocks are here. So if I write my own block, it's going to be in the second part of the binary. So here it's good for us because we know these things. These are unique to the binary, but these are across all binaries, right? So we can differentiate the two. With regards to memory mapping, every vendor and every actual implementation of every device uses its own memory map system, right? However, the Codesys environment, because it supports so many devices, we managed to decrypt its database and collect automatically all the memory maps used by all devices. So we know for the WAGO, right? So we know for the WAGO that these are what's coming to the input and what's leaving for the output. So if we observe what's going to those locations, we can understand exactly where your sensor input is coming in and what the actuation output is coming out. And we can use it to inject our payload. To extract those memory maps, the Codesys has the TRG files that are encrypted. Encrypted means that they have it's a one-time pad gone wrong, which is a one-time pad always. They have one key, and they XOR it. It's 256 bytes keys, but these keys just replicate it, right? So once you start making connections between different files and the different components, you can very easily find the key. So it's supposedly encrypted, but we very easily reverse engineered it. So from those target files describe how each device works uniquely. So what its own memory maps, its own unique characteristics, so we can automate that process too. So eventually you get something like this, which says what is the version of the firmware, what kind of characteristics it has, and gives you some more information you can use while you're dynamically creating a payload. But what's more interesting, what we got mostly from this process is that, remember I mentioned those PRGs have their own unique libraries. Like again, like standard C, you can get printf without the need to type it yourself. Here you can get PID without the need to type it yourself. And this because these are fixed, they appear in those TRG files, right? So once we decrypt that, and we have it in our database, now we can start mapping things in the binary that we know that exist, right? And once we do that, we can identify the exact functionality of the binary. In order to create a signature, because we don't want to compare line by line, but we create signature instead. So we take the opcode sequence, and we hash it, and we store this as a signature of the function. So we do that for the functions as well, and then we compare to our database, and we know that's a PID because it matches the signature in our database. So this is what you get out, the visualization part, and I think what's the most interesting part here is the ICSRF tool we published gives you the ability to understand more unique things, like what is the pressure, what is the integral, what is the derivative. So in this case, we had to do symbolic execution in order to understand what kind of parameters are passed to the functions, and actually all of them are going through the stack. Remember, no optimization. They just do the same safe thing over and over, right? So things go to the stack, and once we see that, then we can start understanding what corresponds to what. So we can give back to the user of the tool that, look, this binary has a PID loop, and this is where the P is, and that's the value of P. And we also further allow the user to change the values of those parameters through this binary modification. So again, this is a proof of concept of what you can do given the information you get from the tool, right? You can change the P again from 0.11 to 0.11.1, right? And that may be a small change in terms of real world thinking, but in a process like a 0.0001 can mean a lot, right? Can actually destroy the process completely. So that's why you also need further intelligence to understand what the new P or the new I should be. So I'll quickly finish because I'm out of time. So you can find the tool online. One example we created what we call red team in a box. So this is an automated payload generation and delivery mechanism. So it does all the steps I described in order and can change the process. In our case, the Tennessee man, it makes the reactor pressure go up to an extent that it would have been destroyed, but of course there are physical alarms right in place that they would stop that from happening, but it creates problems for the process that we know what they are. So in this case, this delivery mechanism you scan the network, through our fingerprinting mechanism, you identify the devices, and then you fingerprint the PLC, you know it's a WAGO, you log in, as expected, there are hardcode credentials everywhere in the RCS world, same case with a WAGO device. You download the binary, you reverse engineer with our tool, the tool gives you back the PID functions, you modify the PI, you change the values as I explained before, and then you have to package the binary. And the binary there's a CRC that's mostly for integrity, right? Let's not blame them for poor security. CRC checksums are for integrity. So we also need to update the CRC and then send back the binary and for execution of the new binary. And if you do that, we showed some sample scenarios that if you play with the reactor, you can either change the pressure to go up and potentially explode. But you can, more interestingly, you can actually cause it to go down. And this may not be noticed. It will just decrease the performance, so you won't be producing your product efficiently. So that's the most stealthy attack, right? So you can reduce things a bit that will incur financial losses to the company, but this will be accumulated over time. So you can, in desalination calculated, you can stay within operational parameters and cause more than $5 million damage a year. So that's the results I've been mentioning, that you can cause it to go down or to go up by changing. So this is by changing the P parameter, the proportion, and this by changing the I, the integral. So I'll finish here. The last thing I'll say is that to make it persistent, you cannot just change something once, right? You have to somehow make it stay there. And we had an example that we demonstrated at Black Hat, and it was part of the hardware CTF we had in the power grid in the US. This is the Z device used. It's a feeder management relay. And when was this? This was a 1990s device, right? And it has authentication, but the authentication is homebrew encryption in a sense by General Electric. When we reported the vulnerability to them and said, hey, why? Well, they said nobody cared, right? Z was the first one who actually did something. Nobody was doing anything. So you can't blame us if in the 90s we actually tried to do something, right? And they had a good point. And they said, these devices are very old. There's nothing we can do about it, right? So maybe it was a way for them to make people buy new devices. So in any case, these are still deployed, and that's why we have them, because they are deployed. So in that, part of the challenge of whoever will solve it is that you can actually, through Modbus, you can get the passcode. The passcode is the encrypted password that you can use. You don't know what it is, but you can see its encrypted form, encrypted. So in our case, we have, in order to change anything, you have to authenticate. But it's weird, to get Modbus registers, you don't need to authenticate. So we can get the passcode, and if we can reverse engineer that, then we can use it to authenticate back and change things. So that's what we did, actually. That's what we reported to the DE. We worked more than a year and a half with them, and we finally, after 2 years, we published a Black Hat 2 years ago, that vulnerability we discovered. But again, the idea is whoever solved the challenge, right? It's a very poor implementation of a block cipher with no initialization vector and linear transformations, right? This is like, the checklist of don't do things, they followed each step, right? No IV, linear transformations, they did all of them, and that's what they came up with. So that picked up a lot of traction, actually, when it was reported, and then BBC, Reuters reported on that. It was big for us, too. It became pretty scary at the point. It became too annoying. When journalists pick up stuff, they may blow them out of proportion. That created issues to us and our industrial partners. But, I mean, there are many good lessons that we got out of this experience. So I don't think I would ever go to Black Hat again. So I'll stop here. I think I'm past time, much past time. But what I want to finish is that at NYU, which is a few kilometers away from here in NYU Abu Dhabi, we have our smart city test, but I only showed a small part of it. That we have for the smart grid, we have industrial IT, you saw the chemical desalination, we have traffic lights, intelligent transportation, and devices that typically appear in a smart house, smart building, like fire alarms or access control cards. So it's open to everyone. You can come and hack, come and play with the devices we have there. We're very happy to have you over. So if you need more information, that's my Twitter account. I'm not posting much, sorry. I'm mostly lurker. There are people here who are actually much more good at producing content, right? I mostly follow stuff, but you can follow me to make me feel happy. But the tool is here. You can download it and play with it. We're very happy if you do it. And you can find information about the G I mentioned in the Black Hat talk in 2017. So that is from me, and I don't know if there are any questions.